I'm going to talk about selection sort. This is another way of taking a list or an array of things that are comparable. That is, if you can compare, what is greater than, less than, and putting it in a sorted order. So, big picture, how does selection sort work? Let me draw out this little picture here. Most sorting algorithms of this variety, you have the idea of, you start with this, part of your array is sorted and part of it isn't, and you're just trying to, one step at a time, increase the sort of portion or partition of your array that's sorted. To get it started with, you just assume the partition is just empty, it's just nothing. So let's say we have this, at each step, this prefix of the array is already sorted. Now we come to the next value. What do we do with it? How do we sort it? Selection sort will look for the smallest value and the rest of the array and swap it into this spot. Note that it can include your current index. So that's it's everything. It's going to be everything. I'm going to say like after this line. It looks a little awkward. But yeah, everything in the unsorted part, it's going to find the smallest value and move it there. And now, that sorted sort of partition is just increased by 1. So let's work through an example. I'm going to write out an array here. I use the same example for my insertion sort video. So this is very similar to insertion sort. It's just insertion sort takes the value from the current value and tries to put it into the right spot in the sorted partition, where this tries to grow the sorted partition by finding the next smallest value, moving it down adjacent to the sorted part. So let's have a couple variables over here. We have I and j used for indices. I'll write out the indices here. Oops, can't count. That's awful. Okay, 2, 3. Let's start planning ahead. 3 is going to come up a lot. Now, we'll start at 0. Now we're assuming, none of the array is sorted. So what we're going to do is selection sort's going to run down the rest of this array. Well, up into including the current value, find the minimum. So it's find the index of the minimum value, then swap it with the current spot. So the minimum value, so maybe I'll put up here. J is, I'll say the min index. It's not a good day for my penmanship, apparently. So that, since 1 is the smallest value, it's at index 3. That's why I'm setting j to 3. So we're just going to swap these values. So I'm going to put 1 here, 5 here. And that's the end of that loop. So now we move on to I is 1. We move on to the next value. We look for the smallest value from 1 to the end. Well, that's going to be also at 1. So we swap through with itself. That's kind of basically a no operation, nothing really to do. So now we move on to I is 2. So from 2 and beyond, what's the index of the smallest value? Well, that's going to be at 3 because 5 is the smallest. So what we'll do is swap those out. So 5 and 9 disappear. So we'll put 5 here and 9 here. That concludes that round. So now we move on to I is equal to 3. Let's look further down the line. Well, the value at 4, that's 6, is smaller than 9. Put that here. So let's swap these. And now we technically could do 4 and just, there's nothing else really compared to. That's not really needed. It's not going to hurt. But there we go. We've sorted the array. So selection sort, another way to think about this is it's just going to keep finding, it's just repeatedly finding the smallest value. You just shorten up the range each one step at a time. So it's find the smallest of all the values, put in the front. Okay, now find the smallest of all the remaining values. Move it up to the front. Now just keep repeating. Find the smallest of all those remaining values from from 0 to 1 to 2 to 3, etc. Let's take a look at. So I've implemented this in Java. Let's take a look at it. It's really sort of very simple implementation. It's very sort of lovely in that way. So I'm passing in the array. I have a couple lines printing out the array just for demonstration purposes. Oh, whoops, jumped down. My cursor is at the bottom. So this is going to be, as I walk through it, I. So this goes through each position in the array. I wrote another method to just define the smallest. Basically at or after a given index. I should have called it like find smallest after or something like that. So that's really just it's going to return the index rather than the value itself, the minimum value. But it's essentially just like calling minimum on an array, but we're just kind of shrinking it down one step at a time as I loop through. So yeah, so find smallest is just going to look for the smallest value at or after I. And then I have another function here that swaps. So we'll swap those and you just repeat this. Let's take a look at find smallest. So again, it's, if you're familiar with, if you've written like a, find min kind of method before, I just assume the smallest values of the starting index. Then down here, I start at the starting index plus 1 because I don't need to, I can kind of shave off one little piece there. I could have it be I is equal to start index. That's okay, but I'm going to go through all the rest of the values. I just simply compare is the current value at I, if it's less than the the index of what I think the smallest value is. If it's smaller than that, then we'll update. So min index is the index of the smallest value so far. If we find a smaller value, then we remember what the smaller value is. And finally, we just return what that index is. And then let's just take a look at swap. Swap is pretty trivial. So we just use a variable to hold the one value, move the value at j into I, and then take the value of the holder variable and just drop it in the j spot. So yeah, it was pretty nice. Writing this up, actually, this is me just bragging, did it exactly correctly the first time. That's always nice. It's nice once you get to the level of, well, hey, I can just code this thing and there's no problem. And then I have this other function here. It's just printing out the value of the array in I and j. So this will hopefully show you step by step what's going on. So if I go back up to my selection sort code, I print off this -1 case. This is what it starts with. And this will just trace through what I did by hand. So we're at the 0th spot. Index of 3 is the smaller value, then it's swapped. Now we're at spot 1. Index 1 is also the smallest, so there's no real change. Now we're index 2. Index 3 has a smaller value, they're swapped, so we get this. Now we're index 3, which is 9. Index 4 is a smaller value, so they get swapped, and then we're done. Well, I have one extra round like I had there, but it doesn't really matter. And that's it. So it's just repeatedly calling essentially find min, and we're just reducing the range that's working over each time. It's a nice, short, simple sorting algorithm. Let's just talk about how long does this take to run. So in computer science, we're always concerned about how an algorithm scales. I'm going to scroll down just a little bit. Because we have this structure of, you know, for goes I up to, say, n is the length of the array. In the worst case, we have for, I also to n, where I could be 0 again. So this is going to run kind of about n times. Oh, maybe that's exactly that's exactly n times, and this one's about all n times as well. So the whole runtime is going to be about n squared. We call this big O n squared, because it's a way of pessimistically bounding the amount of time. So we're saying in the worst case, this means we'll have to, so in the worst case, we'll have to run about, the runtime is going to be approximately related to the size of the input squared. So as the size of the list goes up, we expect, if this is, size of the list, n, this is t, we expect the runtime to have that kind of shape. Because we don't care about, or let's say because everyone's got different chips in their computer. Someone has, I have an AMD processor. I have a Intel Xeon. I got this year's edition. I have the last year's edition. There's all these changes in hardware. Because of these sorts of differences and little differences in implementation, we really care about the most dominant term. So you could think, well, if you actually walk through this step by step, exactly how many steps is this taking? Maybe you could come up with a more precise number. But for the sake of comparison, we just want to sort of, throw out all those little small differences and just look at the broad shape of how this scales, and that's n squared. So we call that big O n squared. So this is, if you recall the insertion sort, this is in the same sort of time complexity category. So they both take an n squared amount of time, meaning they're roughly equivalent, at least in the worst case. So that's insertion sort. Thanks for watching.